A Symmetric Key Cryptographic Algorithm by Holden Surratt,
Stephen Cox,
and Zachary Meyer. For our program, a user would enter their input, which would be any kind of character up to a total of 64 characters. The algorithm would then run, and the user plain text would be encrypted, and a ciphertext would be displayed on the screen. The encryption scheme is fairly simple. First, with the given character, the ASCII value is generated, and then with that ASCII value, we make the corresponding binary value, and we expand it to 8 bits. We pad the most significant bits with zeros. Then we reverse the 8-digit binary number. We take a 4-digit divisor. In our case, we used 8 as displayed on the screen. We divide the reverse binary number by the divisor, and then we store the remainder in the most significant bits and the quotient in the least significant bits. And we pad either one with zeros if they do not meet the required length.
Talking about the decryption of our algorithm, first we multiply the last 5 digits of the ciphertext by the key. Next, we're going to add the first 3 digits of the ciphertext with the result of step 1. Next, if the result of step 2 is not an 8-bit number, make it an 8-bit number, and you can do this by padding it with zeros. The resulting binary number needs to be reversed, and lastly, we convert the reverse binary number back into a character. Some of the advantages of this algorithm are how simplistic it is. It is not very hard to implement, and it's ideal for small amounts of data. And here are the sources that we used for writing our program and compiling our documentation.
Okay, here we are, and we're going to do a quick rundown of what the code looks like. So, we start pretty basic. We initialize a binary string to contain our bit pattern, just to make sure we have space for it. We get the input from the user here. Here is this whole loop handles working with the input and changing that and getting the binary value and setting the binary string from the user input character, and then that will run through with each character they input. And then here we have the for loop that flips the entire order of the binary bit pattern, and then it is stored in the flipped matter, and then we go ahead and from there we divide it, and then another series of checks to get it back out of the binary bit pattern and back into the ASCII value where it's outputted. Okay, we're over here in the program. I'm going to run through it real quick with just a test character. Alright, so our plain text in is just the character T, so that's our ASCII value of the letter, which is the first step right there. The next step is to get that binary value, which is there, and then you have to third flip that whole binary bit pattern around, and then you take a 4-digit divisor key, which we're going to use 1000 here, and then go ahead and divide that, and then that spits out your ciphertext, which is the remainder in the first 3 digits from that division and the quotient in the next 5 digits. So then you take that binary pattern, turn that into a decimal, which is your ASCII value, and here we have 69, which is capital E.